Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review everything covered in week 7. So we're looking at normal distributions, which are also called bell curves. So normal distributions always look like this. They have a bell shape, hence why they're colloquially referred to as bell curves. So the mean is always right in the middle. These distributions are always symmetrical, and we talk about their mean mu and variance sigma squared. So there's a special type of normal distribution where the mean is 0 and both the variance and standard deviation are equal to 1. We call that the standard normal distribution or the Z distribution. So the Z distribution has this very complicated PDF because it is a PDF. That means that the area under the curve is equal to 1. Now, it turns out that for this standard normal distribution, there are 34.13% of scores are within this range from 0 to 1. In fact, that's sort of true of any normal distribution. For any normal distribution, 34.13% of scores are between the mean and one standard deviation above the mean. And because it's symmetrical, there's also 34% between the mean and one standard deviation below the mean. And if we look over here, there are 13.59% of scores between 1 and 2 standard deviations below the mean, and also between 1 and 2 standard deviations above the mean. So these numbers are going to be very useful in solving probability problems. Let's look at some examples. So to solve probability problems, we first need to know how to convert to a Z-score. So if you have a normal distribution, mu is the mean, sigma squared the variance, you can convert a score from this distribution into a Z-score using this number, x minus the mean over standard deviation. The Z-score tells you how many standard deviations from the mean that a score is. And we're going to use this and that picture I showed you on the previous slide to solve probability problems. So it's important that the original distribution was normal, because if that's true, then the Z-scores will be normally distributed. All right, let's say IQ scores are normally distributed with mean 100 and variance 225. So that means that the standard deviation is going to be the square root of 225, which is 15. So what percentage of people have IQ score between 85 and 130? What I'm going to do is convert 85 to a Z-score and 130 to a Z-score. So if I want to convert 85 to a Z-score, I go 85, the score, minus the mean divided by the standard deviation. So 85 is a Z-score of minus 1. That means if your IQ is 85, you are one standard deviation below the mean. Similarly, for 130, I take that score minus the mean and divide by the standard deviation, I get 2. If your IQ is 130, you are 2 standard deviations above the mean. So how does this help us with probability calculations? So we can use that picture on the previous slide. We actually found that there were 34.13% of scores between -1 and 0. Then there were 34.13% of scores between 0 and 1. And then there were 13.59% of scores between 1 and 2. So this is the percentage of scores in a normal distribution that are between -1 and 2 standard deviations from the mean. So adding that up, we get 81.85%, or about 0.82 probability. That means 82% of scores, of IQ scores, will be between 85 and 130. So what about this one? What's the value of K such the probability of having an IQ above K is 0.9987? Well, remember on the previous slide where we saw the normal distribution, there was 0.13% of scores that were above 3 standard deviations. So that means 99.87 of scores in a normal distribution are less than 3 standard deviations from the mean. So here, 3 standard deviations from the mean would be 100 plus 3 times 15, which is 145. If you have an IQ of 145, you are 3 standard deviations above the mean, and because the scores are normally distributed, that means that only 0.13% of scores will be above this. So the answer for K is 145. All right, let's now tackle a slightly harder problem. So let's say I pick a year 12 student at random and let X be the amount they can bench press, and we're going to assume that X, the amount they bench press, follows a normal distribution. So it's known 15.87% of students can bench press more than 67, 97.72% can bench press more than 40, and I'm going to find what percentage of students can bench press at least 45 kilos. In other words, if I select a student at random out of these year 12 boys, what's the probability they can bench press at least 45? Now, I really can't answer this last question here without knowing the mean and standard deviation of the amount students can bench press. So let's first find that. So it's a normal distribution, so 50% of the scores will be above mu, the mean, and 50% will be below. So I'm told that over here I have 67 kilos, and the number of people that can bench press is 15.87%. So the trick to this question is knowing that 15.87% of scores are above mu plus 1 standard deviation. So whatever the mean plus the standard deviation is, it must give me 67. On the other hand, I'm over here at 40, so I know that that's going to be below the mean, and there's only 2.28% of students that can bench press less than 40 kilos. So if we remember what we learned on the first slide, 2.28% of scores were below 2 standard deviations from the mean. So 40 is mu minus 2 standard deviations. So we now have these two equations that we solve simultaneously, and it's actually really easy to do that. We just subtract one from the other. So mu minus mu is 0, sigma minus negative 2 sigma gives me 3 sigma, and 67 minus 40 is equal to 27. So we've got 3 sigma equals 27. Sigma, or the standard deviation, is 9. So that means that mu is equal to 58. So I found the mean and the standard deviation, but how can I find the probability of bench pressing at least 45 kilos? See, the problem here is this. If I convert 45 to a Z-score, 45 minus 58 over 9 is actually negative 1.4 recurring. I didn't have a graph on the first slide that told us, how many scores were above minus 1.4 standard deviations. We actually can't easily find this area here, the probability students can bench press more than 45. So when you have a Z-score that's not a whole number, we need to use our calculator. So we go to the distribution menu and pick out normal CDF. So when I call this function on my graphics calculator, I need to input the lower value. So here it's 45 because we're finding the probability that X is greater than 45, X being the amount that the student can bench press. Now, what would I put for the upper limit? Well, saying X is greater than 45 really means X is between 45 and infinity. Normal distributions can go from minus infinity to infinity. There's no upper or lower limit on the values they can take. So I can't put infinity in my calculator, but if I put the number 10 to the 99, that's about as big a number as your calculator can handle. That will give us the correct probability. So this is my upper limit. I'm putting 10 to the power of 99 in because it's like infinity. And then I need to put in the mean and standard deviation. And then my calculator returns the value about 0.9257. So about 92.6% of students will be able to bench press at least 45 kilos if the mean's 58, standard deviation's 9, and it's a normal distribution. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.